So we are now recording, which is good because I've done nothing important. All right, let's go to the lesson 18. Linear regression. Okay, so the topic for today, and actually the next few class meetings, is on a particular type of data modeling. And this type of data modeling goes under a variety of names, but regression is probably as common a name as any to describe what we're doing. So what we're attempting to do is build prediction engines from our data using various models of how that data is expected to perform. So up until this point, when we were doing normal distributions through Weibull plotting positions of data, gamma distributions through Weibull plotting positions of data, and so on, we were playing the same game in a sense. Our data model was the normal distribution, or the Weibull or the gamma distribution, or the log normal distribution, or the extreme value distribution. That was our function, and then we fit it. In that case, we fit it using statistical methods of sample means, sample standard deviations, sample skews. And when we fitted it and plotted everything, we were, in many cases, rewarded by having the red curve go nicely through the blue dots. And I will keep that mental model going for a while. And if you don't like red curves and blue dots, do blue curves and red dots. It doesn't really matter. One of the other examples that we have explored already was taking a straight line and trying to pass it through a collection of blue dots. And we intentionally built the blue dots to have some curvature. So there was a purpose to that, was to show that there's always some differences between our model and our observations. Those differences go by a lot of names. Perhaps the most common name is the error. There is no value judgment. Error is just the distance from a model to an observation. So we're going to continue on that. And the overall idea of regression, or of data modeling in general, is to assess the following kinds of questions. First, does a set of predictor or explanatory variables, the modern terminology is called a feature, damned if I know why it got that name, does that set do a good job in predicting an outcome, or a dependent or a response variable? So does our prediction engine work? And if so, how well does it work? Second relevant question, which features or explanatory variables in particular are the significant predictors of the outcome variable, and in what way do they, indicated by magnitude and sign of the beta estimates, impact the outcome variable? So let's take just a thought example of that. Suppose we have a prediction engine that has two variables in it, the latitude and longitude of a vehicle and the number of ships in San Pedro Harbor that are waiting to dock. And that, for those two variables, our prediction engine tells us how fast our vehicle is traveling. So of those two variables, does knowing how many ships are offshore in San Pedro Harbor have any reasonable chance of telling me how fast I'm driving? So let me get the chat box open, or you can unmute yourself and state an answer. or you can sit there in silence and I will take a 5-minute break and then return and continue. So, does knowing the number of ships offshore in Los Angeles Harbor, I'll move a little bit north, tell me how fast my car is going?
No.
Yeah, we're getting a lot of no's, and you know, that makes sense. It seems almost evident that the number of ships offshore has nothing to do with how fast a car is going. Does knowing where the car is physically located at a moment in time give us information on how fast it's going? You could also say no, but it certainly is a more useful input, because if we know where we are at 2 moments in time, a short period apart, we can figure out how fast it's going. So in that particular thought example, the number of ships offshore is an insignificant variable. It has no value. Whereas the local position of the vehicle is a very significant variable. It has value in our prediction engine. And we take those ideas to a greater extreme in the second question, which is to explore the value of a particular predictor variable. The reason we want to do that overall is predictor variables that have no value, we can take them out of the equation. By doing that, our consequential arithmetic is easier to manage. And bear in mind that generally, although we're going to be using toy examples through most of the next few lessons, generally these models are applied to what we would consider huge data sets, millions of entries. So removing a useless variable has quite a bit of computational value, because that's millions of things that don't have to be computed. Another question related to regression is, what is the predicted or the estimated value of the response under various excitation conditions? And we've actually explored that. You did it on the exam that you've handed in, where we looked at speed versus time, and you were asked to predict what the speed of the vehicle would be at 15 seconds. That is exactly this question. What is the predicted value of the response? And then related to that question is, what is the uncertainty? So we maybe get a speed of 165 meters per second. We want to know, is it 165 meters per second? Is it 172 meters per second? Is it 151 meters per second? Does that interval represent a 95% probability of whatever the true speed is going to be? So that's an interval estimate. And that's very relevant in the regression approach. So these estimates are used often to explain the relationship between one dependent variable and one or more independent variables. Let's start with what is stated to be the simplest form, although that's a lie. The second simplest form is a linear regression equation with one dependent response variable and one independent explanatory variable, and it's defined by the formula y sub I equals beta 0 plus beta 1 times x sub I, where beta 0 is a constant and it's called the intercept. Beta 1 is a regression coefficient on the independent variable x. It's the slope. So we saw this before as y equals mx plus b. It's the same equation, different letters of the alphabet. And x sub I is our independent or predictor variable. So next we're going to look at the purpose of linear regression, some background, and then we'll look at it as a linear system. And then in lab, you will get to play with some of these ideas. So our 3 objectives for today are to create linear regression models from data using primitive Python structures. And then we'll create linear regression models from data using NumPy and Pandas. When we switch from primitive Python to NumPy and Pandas, we will condense 16, 18 lines of script into a single statement, pandas dot fit, something like that. And that will be of some consequence in practical application in the future. Everything we're going to do in NumPy and pandas today and for the foreseeable future can be done in Python base, but it takes more work on the part of the human being. The computational thinking concepts that are involved include abstraction. The linear model is the abstraction. Decomposing the problem, identifying response and explanatory variables is decomposition. And then data representation either by primitive arrays, vectors and matrices, or NumPy arrays, vectors and matrices. So proceeding forward, let's pose a couple of fundamental questions. What is regression used for? Why is it useful? The second one is possibly of relevance to you right now because the easy answer is it's useful because it's on the syllabus, but we'll probably get more useful explanations for that. The three major uses of regression analysis are determining the strength of predictors, and not strength in a structural engineering sense, but how valuable a predictive variable is to a prediction. Forecasting in effect. So when we changed the time in our linear model on the exam, we were forecasting a speed. And the other way of forecasting is something called trend forecasting. And in trend forecasting, we are less interested in the actual value of a prediction than we are in what the net change is. So if we double a predictor variable, do we expect the behavior of the prediction to double or triple or what have you? So in the first case, the regression can be used to identify the strength of an effect in the independent variable has on a dependent variable. Typical questions are, what is the relationship between dose and effect? How big of a COVID shot do you need to generate enough revenue for the drug company as well as a therapeutic effect for the patient? Sales and marketing spending. How much money do we spend on our YouTube ads and annoy potential customers compared to how much crap we sell via click-through? What is the relationship between age and income? Do babies have a greater income than grown-ups, or more importantly, greater potential cumulative income? And that's an important question because if you're running a government, you want to tax that income. Secondly, we can use regression to forecast effects. That is, it will help us understand how much the dependent variable changes with a change in one or more independent variables. So that would be a question to ask something like, how much additional revenue do I get for each additional $1,000 spent on marketing? And that's a real question somewhere. I'm sure that question is being asked right now as we speak somewhere, maybe with some slight changes in the wording. Somebody wearing a suit is asking somebody who's trying to keep their job, why should I waste $1,000 on my billion-dollar company? And if someone who's trying to keep their job is going to say, sir or ma'am, because if we spend that $1,000, we'll make $2 billion in 2 weeks. And if they're fool enough to believe that, today being April Fool's Day, so you can say silly crap like that, you would have to defend that somehow, and a regression analysis might be the tool you choose to use. Third, regression analysis can predict trends in future values. We can use it to get point estimates, which is what we did with the speed versus time. A question might be, again, from the field of making other people's money yours, what will the price of gold be in 6 months? In fact, if you had a prediction engine that was very accurate at answering that question, you could pretty much quit your engineering career right now, run that prediction engine a few 6-month sequences, and 2 years from now, you would be cruising in your private yacht at some desirable place and never have to think about Texas Tech again. But the probability of that, while not zero, is interaction time.
Low.
Yeah, low. Good answer. So here is a, continuing on with our line of thinking, here is an excerpt from a Texas Instrument 55 calculator. And let me see if I can find one here. I think I've got one here at the desk. Well, I can't find it right now. So these are pretty old school devices, but back in the olden days when dinosaurs roamed the earth, probably before many of you were birthed, we had to do what we're going to do today in a somewhat more manual fashion. And from this old user manual, let's read what it has to say. In many disciplines, it's desirable to express one variable in terms of another, even though the variables are independent and not necessarily analytical functions of each other. That last part of that sentence is pretty important. We're going to be passing a line through a bunch of dots. When we do that, our data model, the line, we are making the assertion that that is an effective predictor of those dots, but there's no requirement that there actually be a relationship. An accepted practice is to perform a least squares linear regression, which is designed to minimize the sum of squares of deviations of the actual points from the straight line of best fit. In practice, we're essentially constructing a plot of variables called a scatter diagram. Have you heard of scatter diagrams before? That would be a yes. Excellent.
Oh,
Yes, sir.
Thank you. A scatter diagram and drawing the best straight line which uniformly divides the data points as shown below. So if you have 1, 2, 3, 4, 5, 6, if you had 9 data points that fall like that, that apparently is the best line that you could get. Although if I drew the best line and you drew it and the entire class drew it, all 60 of you, it's quite likely we would get 60 different lines. And so that kind of defeats the concept of best. What we're looking for is some systematic method that when I draw the line and you draw the line, we get the same line. And we declare that the best straight line. And that method is ordinary least squares. We have the added bonus feature that because the data may not be a straight line, we have to also measure how well the linear curve or affine function fits the data. This measure is called the correlation coefficient and can be calculated from the independent variables in the linear equation parameters. You will get very familiar with correlation in lab today. So I will, other than just stating how to do it, we will save that for lab. In the context of our class, the straight solid line in this figure is the data model. The particular data model in this figure has the structure y is equal to beta 0 plus beta 1 times x, where x in this case is the left-right axis, and then y is the response, the up-down axis. The ordered pairs x sub I, y sub I, so each of these dots is called an ordered pair, xi, yi. In the scatter plot are the observation, or foreshadowing to future lessons, the training set. As depicted here, the value y is the response to different values of the explanatory variable x. The typical convention is response on the up-down axis, but not always. Keep that in mind. In some instances, the axes will be rotated, but that is for a later date and time. Usually, the up-down axis is the response, and the left-right axis is the predictor, or the explainer, or the feature. The model parameters in this instance are beta 0 and beta 1, which you know as intercept and slope. And the reason we've switched to Greek letters of the alphabet, it has advantages later on because we can add more and more variables and just change the subscript rather than create names. Slope, intercept, curviness, wiggliness, sinuosity. We want to get outside of that. So classically, in old school statistics class, we would introduce things called normal equations and find the model parameters by solving a set of normal equations where beta 1 is equal to the sum of all the x's in the observations times the sum of all the y's in the observations minus how many things there are, n, times the sum of the product of each x and each y, divided by the sum of all the x's, quantity squared, minus how many things there are, n, times the sum of the x squares. And expressed in that way, you all could code this right now. I'll just say in advance, it's not an efficient way to do it, but it'll work. And then beta 0 is the mean value of the y observations, y bar, minus that computed value beta 1 times the mean value of the features, x bar. Okay, so we've got the normal equations presented to us without any kind of proof. You will get that in your statistics class at some point. Let's just go ahead and pretend that it's correct. We're just going to apply this. We're going to use our Python scripting skills, and we'll do classical regression using the normal equation. So the two lists from the Texas Instrument user manual, one of them is here, and here's the corresponding one that goes with it. So I think it's on page 41 of the manual, which is not duplicated here. And we're going to use this approach to find the slope and intercept using the values from the TI-55 user manual. Since we're dealing with plots, we're probably going to want our own plotting package. And so we're going to go ahead and create this thing called Make-A-Bear. Now, what is Make-A-Bear?
It's a little store that you find in a mall. A lot of kids go to it. You like make your own little bear.
Okay, that's one. I think that's called Build-A-Bear. But
yeah,
what I have highlighted here, what structure is that?
It's a function to create a chart.
Excellent. Thank you very much. It's a function. And we even have some comments here that are kind of telling us how to use the function. It says it's a plotting function dependent on matplot library installed above. Looks like I import it every time I call the function anyway. The x values and y values are data pairs to feed to the scatter plot. They have to be floats, and they probably should be lists. Let's see. Yeah, they need to be lists. And it has a value x left and y left, which is the left endpoint of the line to draw, also a float. X, y, right, y, right, right endpoint of a line to draw, also a float. X label, Y label, those are strings. Title, a string. So there's our plotting package. Kind of like our make two plots, but different name. And why did I name it Make-A-Bear?
Because you like bears.
Oh, close. That's close enough, Abby. Yeah, because the name doesn't really matter. As long as I know what name to use, it'll be just fine. So I'll apply the principle of algebraic substitution, and we can change that if we want. And now if we actually just look at the function rather quickly, we import the plotting library, we build a scatter plot, and then we build a line plot. We throw the labels on it, X label, Y label, title, and then the show command renders everything. And then we return to whatever our calling program is. So let's run that, and hopefully, okay, that was sweet, no complaints. And now we'll actually do the Texas Instrument 55 example. In that particular example, they were looking at fiber reinforced polymer. Those were numbers from NASA. And what they had discovered was that the length of a fiber and its weight were related. That kind of makes sense, but a long fiber had a higher weight than a short fiber. And so for whatever reason, we're going to see if the length versus fiber weight has any meaningful linear relationship. So what we're going to do is we're going to make the two lists, and then we'll plot the two lists, and then I'm going to arbitrarily choose to make the left endpoint 580 and 96, and the right endpoint 630 and 106, and then we have some labels here. So let's hope the plot works. Okay, there we go. So we've now drawn a red line on blue dots. In this case, the red line is a dashed line. How did we get dashes? We got it right here. And let's suppose that we like that line. We can stipulate, okay, that is our prediction line. So now if I have a 100 centimeter long piece of fiber, what do I expect it to weigh? 100 centimeter, not 100 meters. That'd be a big piece of fiber.
Around 600 grams.
Yeah, I would go to the 100, draw a horizontal line, read down around 600 grams. So for a 1L, that's easy enough to do directly from the chart. And what have we done prior to this lesson when we wanted to do that repeatedly? We would go ahead and build the linear function and just interrogate it directly. So keep in mind, to plot that dashed line, we actually only supplied two XY pairs to plot the line, and those XY pairs have no particular relationship to the blue dots. So let's go ahead and get a colonoscope and find out where the dashed line came from. We can create a function called myLine, although I should call that what's my line, and we'll have a variable named slope and intercept, value 1 and value 2. And what this function will do is return a tuple, x1, x2, y1, and y2 from the formula y equals slope times value plus intercept. And so this function creates two empty lists, y and x, appends value 1 to x, appends value 2 to x, and then appends y1 and y2 using a formula, slope times x plus intercept. Let's go back up here. Slope times x plus intercept. So essentially it's doing this equation with different names. Go ahead and run that sucker. And if we go ahead and put in a slope of 0.129 and 22.83, actually let's jack with those a little bit. Let's say that's my first guess of slope and intercept. And I do that and go, wow, that's pretty terrible, right? The red dashed line and the blue dots, they plotted on the same chart, but that's about all you can say. So operationally speaking, what do we need to do with that red line? The blue dots are fixed. They're data.
Lower the y-intercept.
Yeah, we want to make, correct, we want to make the line move down relative to the blue dots. And so the up-down part of the line holding the slope constant is controlled by whatever value of intercept that we choose. So let's proceed as if we're a computer, and we'll use the bisection technique. So half of 28 is 14. If we do that, our red line will end up below the blue dots. Oh, actually, half of 14 is 7. It is not plotting this correctly. Computer's making a fool out of me. But we play around and eventually we're going to enter a value of 0.13 and 23. And there we feel that we're close. And now we would want to refine things. The first thing we want to refine is we probably want to make our low value a little lower so we can assess this data point. And so the smallest value is, well, 580 should have been good. Oh, our blue dots are plotting wrong. That is weird. Okay, well, I'll go with that. And if we reduce the intercept a little bit, let's see what effect that has. Okay, so reducing the intercept from 23 to 22 has the line kind of passing through. We have 1 point below the line. This point would probably be below the line if it projected. We have 1, 2, 3, 4 above the line. So if we change our slope a little bit, a little less slope, these things are awfully tightly bound. Okay, so you're seeing me change numbers and we can move the line around. That is not a very efficient way to find the formula for our red line. So let me put this back to 13. I don't know why I had a 23 there, but we'll go with that. So let's say we fuss around for a while and decide, okay, that I'm done with that. That's about what I want. Let's look at our endpoints of the red line. We do that and it says at a weight of 580 grams, the model length is 97.4 centimeters. At a weight of 630 grams, the model length is 103.9. So that represents that point and that point. Now let's evaluate the normal equations up here, because we have all the information contained in these equations. We have x's and y's. We can compute these various sums. We can compute the mean of the two collections and structure our slope and intercept based on the normal equation. So here is building the normal equations. We're going to have a variable called sum x where we keep track of the x values, sum y, sum of xy, which is the cross term, sum of x squared, sum of y squared. And initially we just assign them values of 0. And then we're going to do very crude programming here. We're going to use a structure here which is called what kind of structure is that?
A for loop.
Good, correct. And a for loop is what type of repetition? What's our sentinel value?
The length of the sample weight.
It doesn't have a sentinel value. It's called count controlled repetition. We do have a count. So the
Okay.
length of the sample weight determines how many times we will pass through this loop. If the length is 0, we'll get 0 passes. If the length is 10, we'll recover values 0 through 9 and so forth. Okay, so our sum x term, we take what's in the current value of sum x and we add to it the value of sample weight for the ith item. And the values of I go from 0, 1, 2, 3, 4, and so on. So when I starts out as 0, that's the first thing. Sum x is 0. We add the sample weight, and then we put the result back into sum x. There's another syntax we could have used to accomplish the same thing. Anyone recall what it is? We can replace all of that with something else. I know that was so 2 months ago. You could use the plus equal structure, and it has the same effect as this. Sum of x squared, we take what's in the accumulator and we add to it the value of sample weight quantity squared. Sum y, we take what's in the accumulator, we add the sample length to it. Sum y squared, we take what's in the accumulator and we add the sample length quantity squared. Sum of xy, we take what's in the accumulator, we add the sample weight times the sample length. When we pass through this loop, we now have all the pieces of the normal equations. This one's contained in sum x, this is sum y, this is sum xy, this is sum x2. Excuse me, no, this one is sum x2, and there's a, we don't have sum y2, or maybe we do, but we don't need it. And now we just simply evaluate the expression. So the cross term minus how many things there are times the cross term, and that is just the normal equations above, rearranged slightly for computational efficiency. And finally, the beta 0. And then we're going to have it give us a linear model. So now we give it the linear model. Y is equal to 0.129 x plus an intercept of 22.813. Now let's watch what happens when we put that back into our myline function. We run that, and that is now our estimate of the linear model that best explains these blue dots. And what we have just done is applied ordinary least squares. And one way we can evaluate a quality of the model is, on average, there should be about half as many points that plots below the line as plot above the line. So we have 1, 2, 3 below the line, 1, 2, 3 above the line. That's not always a guarantee, but that is a good, quick visual assessment. So that's not a bad predictive model. So the next question that comes to mind is, where do these equations come from? Well, they came from up there at the top of the notebook, or they come from a statistics book, or they come from somewhere else, but I certainly can't create them, which is not true. Let's go back to our linear model. Y equals beta 0 plus beta 1x, and now we're going to add this error term. And that error represents the distance from a point to whatever the current model line is. So this distance right here, we call that error. So in this particular picture, look at point number 3 right here where the cursor is, and point number 4 where the cursor is. Which of those two has the larger error? Distance from the point to the red line. Yeah, number 4. Good, John. Good. Yeah, this one has a larger error. And what we're doing when we're adjusting our red line is to try to we're going to add up all those errors. Well, actually, we're going to square all those errors so that they always have a positive sign. And then we're going to add up all those errors, and we're going to jack this line by changing its slope and sliding it up and down a little bit until we get the sum of errors that's the smallest that's possible. That's why it's called sum of squared errors, or excuse me, minimizing sum of squared errors. So to compute the error for our training set, we can take this equation here. We want to square the errors, and we get the sum of errors squared is equal to the sum of the quantity y sub I minus beta 0 minus beta 1 times x quantity squared. And our goal is to minimize this error by choice of beta 0 and beta 1. So we have this function. that we've just created all by ourselves, no help. And we have two knobs on the function. We have the beta 0 knob and the beta 1 knob. And we're going to twist those knobs until we minimize the function. Recall from your calculus class that the necessary and sufficient conditions for a minimum is that the first partial derivatives of the error function must vanish. They have to equal 0 for a minimum to exist. So we can leverage that requirement. It's fancy wordage for saying we can use that requirement to write an algebraic condition that hopefully we can solve. And if we solve it, maybe that'll tell us how to minimize the errors. And so the first one is we want to take the derivative of the error function with respect to beta 0, which is equal to the derivative of the sum of y minus beta 0 minus beta 1 x sub I squared with respect to beta 0. Keep in mind here we have a b0 squared term, and what will be left is if we take the derivative of this thing, we get 2 times the thing multiplied by d beta 0 over d beta 0, which is 1. So what's left after we perform the calculus is the sum of 2 times the quantity y sub I minus beta 0 plus beta 1 xi. The 2 is a constant, and it can be brought out of the summation sign. So it's now minus 2 times the sum yi minus n beta 0, because there's an implicit 1 in front of here, minus beta 1, which can be brought out of the summation sign, times x sub I. So one of our equations that has to be true to find a minimum is that minus 2 times the sum of y minus n beta 0 minus beta 1 times the sum of x has to equal 0. We repeat the analysis with our next variable. The first derivative of the error with respect to beta 1 is equal to the derivative with respect to beta 1 of the sum y sub I minus beta 0 minus beta 1 xi quantity squared. The 2 comes out when we perform differentiation. And now we have beta 1x left over. And when we perform that differentiation, we'll have an x sub I term remaining instead of just the constant 1. And so we now have 2 times the thing with the x sub I remaining. So 2 times this quantity times x sub I. Perform the necessary arithmetic, that becomes minus 2 times the quantity sum xi yi, the cross product, minus n times beta 0, sum of the x, minus beta 1, sum of the x squared equals 0. So this is our second condition that has to be true. So those two conditions have to be true at the same time. And we can, because there's only 2, we can solve for one of them in terms of the other and just place it into the other and then recover the various variables. So essentially, solving these two equations simultaneously produces these resulting solutions. Beta 1 is that formula, sum x, sum y minus n, sum xy, divided by sum x quantity squared minus n, sum of x squared. Beta 0 is equal to y bar minus beta 1 x bar. So that's where the normal equations come from. They come from requiring that the first derivative of the error function, which is simply the difference between our model and our observations, is equal to 0. We also can apply the principles of computational linear algebra, which has an advantage when we want to make more complicated models. So we can start again with our linear data model, and we have y equals beta 0 plus beta 1 x plus the error term. We'll rewrite it in terms of vectors. So our y vector, shown here as cap y, y1, y2, blah, 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 y sub n. So if there's 6 things, then this is a vector that's 6 units tall. We have our parameter vector, the things that we're looking for, beta 0 and beta 1. There's just 2 of those. And we have our design matrix, which is our cap X vector, which is a column of ones and then a column X1, X2, blah, 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 Xn. What this column of ones represents is when we write this as a vector matrix equation, the column of ones is picking up the implicit one that's on beta 0. So there's a 1 right here. You just can't see it because it's really hiding. And that's where that 1 is. And then the coefficient that's on beta 1 are the individual x's, and they appear right here. And then lastly, there's the error vector. So now if we rewrite our system in vector matrix form, we can write cap y is equal to cap x times beta, the vector, plus error, the vector. And now we'll perform the same calculus as before, except we'll do it by vector calculus. And doing that, it turns out that if we pre-multiply by the transpose of the design matrix X, we'll have a linear system in beta, which we can solve using Gaussian reduction, LU decomposition, or any other equation solving method. So the resulting system that minimizes error transpose error, which has the same identical properties as the sum of the errors squared, is X transpose Y equals X transpose X beta. And we want to solve for beta. The formal solution in terms of notation, we would write X transpose X inverse times X transpose Y. Now, normally you would never actually do the matrix inversion, especially when you're dealing with thousands and thousands of things, because the matrix inversion is unnecessary. Instead, we just solve the associated linear system X transpose X beta equals X transpose Y for beta. So we've seen this before. This is the Gaussian illumination with pivoting in Python. So we're going to define a function called linear solver. And what linear solver takes as input is it takes an A matrix. In our case, the A matrix is X transpose X. And it takes the B right-hand side vector. In our case, it's going to be X transpose Y. And it returns the value of X, which in our case is going to be beta. We're going to need to have the ability to multiply matrices. And so we have a function called matrix multiply. It takes one matrix named A matrix, another matrix named B matrix. We have to tell it how many rows are in A, how many columns are in A, how many rows are in B, how many columns are in B, and it returns a matrix called the result matrix, which is the product of A and B. We also need the ability to multiply a vector by a matrix. So we have matrix vector multiplication. Takes as input a matrix, a vector. Need to know the number of rows in the matrix and the number of columns in the matrix. And then it's going to produce a result vector and perform the necessary arithmetic. And you notice these two functions, these are self-written, so they don't have any error checking. So if we make a computational linear algebra error, the program will just break and we'll get the big old pink screen of death. So now let's build the matrices for our problem. When we perform our X transpose X, the number of columns we're dealing with in our design matrix is 2. So we're going to tell it that our design matrix has 2. The number of rows is going to be whatever the length of our data stream is, in this case, sample weight. Our X matrix, we're going to fill it with ones for J ranging from the column number of X to the row number of X. And then the transposition is going to be row, column. And then the Y vector is going to be the row numbers. And then we populate the design matrix with sample weights, the transpose matrix with sample weights, and then the Y vector with sample lengths. And then we build our X transpose X list, we're going to just start it full of zeros. X transpose log Y is an empty list. And then to populate X transpose X, we perform the matrix multiplication with X transpose times X. We give it the various ranking. X transpose Y is a matrix vector multiplication. We give it the necessary input. Now we're getting to our solution vector. And at this point, you're thinking, why do this? It seems like the normal equations are a lot easier. And I would agree at first glance that's so, but this thing is pretty useful for other stuff. So we have our solution vector beta, which starts out as an empty list, and we're going to apply our linear solver program that we wrote, and from that we're going to get the slope is going to come back as beta 1, and the intercept will be beta 0, and then we'll go ahead and plot my line. Okay, so let me load in the linear equation solver. Done, and we'll go ahead and solve the normal equations by linear algebra. And there is our result, and here is our intercept and slope. Okay, so a couple of things at this point. That was done in base Python. You notice here there was no math package installed. There was no NumPy installed, nothing. This was done in base ordinary Python. So in principle, you all could do that. You don't need Python or pandas for everything. But there's an awful lot of scripting there, and every single one of those lines is an opportunity for us to make a mistake. We're human beings. What are human beings really good at? Making mistakes. So what's the value of doing it? So that point being there is a NumPy equivalent to that. I think it's like 2 lines of code. What's the value of doing it with computational linear algebra? Well, these particular data, they kind of line up, but maybe they have some other components to it. Let's suppose we want to deal with stuff that has curvature. So we're going to make 2 new lists. We're going to make a list called YYY and XXX. And we'll just arbitrarily plot a line that has slope of 1/2, intercept of 1 from -3 to 3. And let's plot the 2. And we get this: blue dot, blue dot, blue dot, blue dot, blue dot, red straight line. That's a useful model of our data, but it's not a very good model of our data. Let's do it again using our linear algebra system. So the only change here from the prior one is what the components are. We do that, and that should be the same. So we get the same there. And now let's go ahead and use our linear solver. And we'll plot it. And, well, wait a minute, what's going on there? Well, I played a trick on you all. I modified my design matrix, and so actually I changed the model from y equals beta 0 plus beta 1x to y equals beta 0 plus beta 1x plus beta 2x squared. I went ahead and put a polynomial in here. And when we do that, we get what's arguably a somewhat better model of these particular blue dots. And all we had to do was add those 2 variables, the x squared term. That's trivial to do in computational linear algebra. Imagine what the normal equations would look like if there was a 3rd component here, beta 2x squared. So you would have 2 times y1 minus beta 0 minus beta 1 x1 minus beta 2 xi squared times xi squared. You would have another group of terms over here. It's actually quite annoying to do in normal equations and rather trivial to do in in computational linear algebra. So we're going to move over to lab in a few seconds. You see here it says now using NumPy. See if I already have it in NumPy. I do not. We'll show how to do this using NumPy next time. NumPy is going to take about 6 lines of code. 4 of them are going to be to populate the vectors, and the 2 will actually be to make the drawing. So I think this is a good stopping point, because looking at the few people who have their video on, you look like you're about to pass out. Abby from lack of food.
Lots of information.
Yeah, it's you won't find this in the UC Berkeley book, so you're getting extra bonus features here. When you're starting to learn this stuff, by all means, when you take your statistics class, go ahead and do what they require you to with normal equations, but keep in mind, you can do everything as a linear system, and it is literally trivial. I'll go ahead and change the appearance of this one. It is literally trivial to do this. I'm actually just typesetting the math. I'll show you what it looks like. Remember, don't save this. Okay, that is n. So doing polynomials is trivial. All I did here in the typesetting was add a column, and that column gets added right here when we're building our equations. In fact, we actually only have to do it once if we could automate the transposition. And now we are passing polynomials. What if I wanted to do a cubic? In terms of our computational linear algebra, there'd just be 2 more lines right here, and we're good to go. So we can, just for grins, since I have time, we'll go ahead and try that.
What about for a log regression line?
Similar type of thinking. We're actually going to do a logistic regression later on. If all you want to do is log transform the variables, you would do that first and then add these. Let's go ahead and put the cubic in. So all we're doing is changing the function, and let's see, that means I'm going to have 1, 2, 3, 4 columns, and I don't think I have to change anything else. Here goes nothing. Come on. Oh, at least give me a pink screen of death. Damn it, I hate it when that happens. While that is deciding to get done, let me untypeset my typesetting. And this is why most of your classes, they never do anything live. Because you look like a fool when you do stuff live. Okay, that's our original thing. Do I have control back? I have a hung system. Interrupt the kernel. Come on. Okay, that was close. Let's see, I haven't. I'm going to do that. Let me get XXX and YYY built. Okay, so now I have the inputs. Now we'll try it with a cubic. None of those are as I've got something wrong. It's not giving me an error message. Well, anyway, never mind. Even though I claim it's trivial, there is something else I've missed. Have to stop the kernel. Yikes, that is one broken script. That happens. Restart. Come on, computer, anytime now. Don't make me mad. It's definitely completely broken right now. Well, that's not the first time that's happened. Let me hand off control to Farang, and you guys can start the lab actually a little early today, which is by plan. And let's see, how do I hand off control? I got to go over here and find everybody. There you are. Everybody's founded.
So if you want to have a break, we're going to begin the lab at 11:15. So a 6-minute break.
You should be able to take the screen now.
Thank you.
I'm going to try to recover my server control. Okay. Okay, I have no kernel.
So no more complaints about the exam.
I'm sure there's plenty of complaints. They're just being kind and keeping them to themselves like they should. Thank you very much.
Trust me, you guys' exam is the least of my concern in terms of complaints.
You're all going to be great lawyers someday because you got that part of life figured out already. And if you perceive that as an insult, it was.
Roger that.
Okay, let's see if this thing. If somebody doesn't mind, if you can go to Blackboard and see if you can access the links to this lesson. Because if you can, then I'm just going to stop doing what I'm doing. If you can't, I need to reboot the server.
The page just starts infinitely loading. I had it loading for a few minutes before you asked us to.
It doesn't do anything. Okay, let me go ahead. This will take a few minutes. I will restart the server. We got tricked by Amazon again because they couldn't find any dollar bills laying around. Okay. Try a soft reboot.
Kellen, the bonus points only apply to the test that they are on.
Okay. Stopping the server. At least it's responding. Yeah, we don't have a secondary market in bonus points, but that's something to think about for the future. The alibi thing is only for people that know what it is. So if you have no idea what it is, just ignore it.
So speaking of slangs, this RIP isn't the same RIP that I know, right? It's not rest in peace anymore.
No.
Okay, what's
Does
it
it-
mean now?
Yeah.
I'll turn off the recorder if it's naughty, but
I thought it was still rest in peace, I'll be honest.
No, they're using it everywhere, so it cannot mean like that. Like
It
It
does
is
mean it.
RP,
It's
okay.
yeah, it's just more casual. It's like, oh, your computer doesn't work. Rip.
also, and you read it as RIP.
I mean, you can say it either way.
Okay.
Like rip, RIP, RIP in peace.
It's like a shorter way of saying like that sucks. But it still the acronym still means the same thing.
I see. It's like, that's unfortunate. Okay, what's wrong with that? That's unfortunate is a very good and easy to understand sentence.
It's
Yeah.
also more syllables there.
Have you heard unlucky?
Unlucky as unlucky, or the slang for unlucky?
Well, I mean, it still means unlucky, but people use it like slang. Like, I mean, like, it'll be like, oh, I failed my test, like, ah, unlucky.
Look,
Unlucky
I
is a little
feel
bit
bad
demeaning.
that they never taught this at school.
they couldn't.
Typically, unlucky is a little bit more demeaning, though. Like, if they messed something up that definitely was not based on luck, you would say unlucky to call out that, yeah, you just messed up.
Okay. And it's different from tough luck.
I'd say so. I wouldn't use them the same.
Okay. Okay, Brandon, that was a good example. So 11:15, let us begin our lab 18 on precognition and other sins of the human brain.
Stall for a little bit because the server's still rebooting, so they can't get
Okay.
to anything.
So I'm going to wait for your signal then.
All right, I'll let you, okay, they should be able to access it now.
Okay.
So you may begin. I'm gonna check my metrics, be sure it has some clock cycles left. Yep, it has 30 minutes of clock cycles remaining, so they should be able to access stuff now. You may have to close and reopen your browser to reconnect.
It's working now, but there is another thing. I was trying to download the lab and the advertising CSV earlier. Whenever I do the advertising CSV, it says failed blocked.
So you can't just right click on it and save item?
Yeah, it won't let me like save link as.
Okay.
It like goes down to the, yeah, I think so. Yeah. I'll keep messing around with it and try to fix it.
Just for the time being, I can put
I'll
it in
put
the
a
chat box.
copy in the chat box right now.
Oh, you will? Okay, thank you.
Oh, thank you. That'll be helpful.
It downloaded fine for me, so it's something else. If it will
Okay.
actually let me get a file, my computer, yes.
Yeah, Harper Hill in chat says it sounds like a local security issue, which is probably the case.
I'm down his alley.
Okay, so advertising is now in the chat box. It's a shows as a 3K file, but it's a 4K block, so it's a pretty small file. So
Okay, let us begin by the amazing and mysterious human brain. Have a look at these sequences, and let's see if you can guess what comes next. So cast your votes in the chat box. A, B, C, D, E. What comes next?
Are you aware that that's slang as well, Farhang?
Come again?
Are you aware that that's also slang?
What, the A, B, C, D, E?
No, just the letter everyone's spamming.
I can imagine.
Well, basically, in one of the Call of Duties, you start the game by pressing F to pay respects over a coffin, and now it's like online slang if you press F to pay respects.
Okay, Okay, thank you very much for shedding light on that, because I had a very bad interpretation of it. Okay.
Nothing
So
bad.
thank you very much for sharing your votes. I think everyone said F except for Wally, who I think was deliberately trying to mess with my problem. Yeah, A, B, C, D, E, F is going to be the next one. Now, 5, 10, 15, 20, 25, what is next? 30, 30, 30. Okay, seems like you all agree on this. How about next one? 2, 4, 8, 16, 32. 64s coming in the chat. Awesome. Now, next one, 0, 1, 1, 2, 3. What comes next? Ooh, we're getting some different answers now.
It's my favorite sequence.
Wait a minute. Are you God?
I don't think so.
It is known to be the sequence of life, or the sequence of God, because apparently this repeats so many times in nature. So do we know this sequence?
Yes, the Fibonacci sequence.
Exactly. And how does it work?
You add the two previous numbers to get the next number in the sequence. So 0 plus 1 equals 1, 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2, 5, 8.
Exactly. And that's how it goes. So basically 3 plus 2, 5, 5 plus 3, 8, 8 plus 5, 13, 13 plus 8, 21, 20 plus 13, 34, and so on. And because of all this getting repeated in nature in a very weird way, it is a very famous sequence of numbers. Okay, how about the last one? 1, 11, 21, 1,211, and so on. I have one answer from Harper. Okay. Come on, make a guess. Caden, what made you change your mind?
I'm just being sarcastic, sorry.
Okay. So Harper, would you like to explain?
Yeah, each number in the sequence describes the one before, literally, I guess. There's 3 1s, 2 2s, and 1 1.
So yeah, you start with a 1, and then in your next step, you read aloud what you see. It's 1 1. And then in the next one, you see 2 1s. And then in the next one, I see 1 2 and 1 1, and keep going on. So for the next one, you see 3 1s, 2 2s, 1 1. Okay, so thank you very much for playing the game. Now the question is, how does your brain do this? How do you guess or predict the next step? Is it the fact that you know these sequences like A, B, C, D, E? Or is it the fact that there is only one possible next step? Or is there something like a pattern or relationship that you detect? Which one is it?
Pattern.
Pattern.
Any other answers? So what is the pattern in A, B, C, D, E?
That one's pre-learned, actually. That's the alphabet. If I didn't know the alphabet, I wouldn't be able to know that one.
Exactly. So it's not always a pattern. Pattern is one of the explanations, depending on the sequence that you're dealing with. Sean, you said neural network. What did you mean by that?
Isn't it? Because I was doing some research on it, but isn't that how they train machines to detect patterns?
Well, that's a long story that you can write PhD thesis on, but the general idea is, yes, you basically train your models and based on a set of observed events and ask it to predict the outcome based on a bunch of observations or features that you have in the future. But generally, the answer to this question was not neural network. Neural networks are predictive models or can be used as predictive models. Okay, what if instead of one single sequence like the ones we did, we maybe have two sets of numbers? Can we predict the next item in a situation like this? Have you ever been in a situation like this where you have like two sets of numbers and you are interested in predicting the next step? Doesn't sound familiar? Harper, that was correct. But guys, take a deep breath. Try to revive some of that dead short-term and long-term memory that you have and think about it. Have you ever been in a situation where you've given two sets of numbers and you were asked to predict a number based on those?
Are you talking about in the class or like just in general in life?
Originally, I was talking about in the class, but because of your amazing performance, now I'm saying if you remember that from any other locations as well.
Oh, definitely.
Yeah, I was just thinking with the subnetting, if you're breaking something up into like a bunch of /30s, then they're all the same distance apart. So instead of having to calculate it out for each subnet, you can just kind of go by whatever step you need to.
Okay, fair enough. Over the past 48 hours, have you seen something similar to this? Blue points,
The only time
red lines.
was when we were trying to match that line to the blue points.
Do you remember this question?
That's
Oh,
what
yes.
Okay. Do you have two sets of numbers?
Yes.
One set for time, one set for speed, where you ask to use a data model to estimate the speed at t equals 15 seconds.
Yes.
Okay, so this is very similar to what we are discussing. In this case, we have two sets of numbers, and we are interested in predicting a number based on these. Now, let us go over some important terminology. Linear regression is a basic predictive analytics technique that uses historical data to predict an output variable. In this example, what is historical data?
The speed,
Just that?
I guess.
And the time?
And the time. So when we say historical data, we are not talking about data coming out of caves. Anything that is observed and has not happened yet is historical data. So we have made some measurements. We used the timer and we said, okay, at time equals 0, speed was 0. At time equal 1, speed was 3. At time equal 8, speed was 77.7 meters per second, and so on. This is our historical data. What about t equals 15 seconds? Is this historic data? Why not?
No, but I don't know how to explain my answer.
We haven't collected any data on it in the past.
Exactly. all we have is from 0 to 10. So anything beyond 10 is not historic data for us anymore. It's something that we need to predict. The predictor variable or input is the variable or variables that help predict the value of the output variable. It is commonly referred to as X. This is the thing that we use to get what we want. This is going to be our input. The output variable is the thing that we want to predict. It is commonly referred to as Y. So in this example, what is X, what is Y?
Your X is time and your Y is speed.
Why? Because the speed is dependent on time. Thank you very much, Jalissa. And because we are asked to estimate the speed based on time. So we know the time, that is our input. And we want the speed, which is our output. Now, if the question was, at what time will we reach 200 meters per second? What would change?
The independent and dependent variables.
Which means, what will be my input?
Input is speed and output is time.
Exactly. So there is no certain fixed definition for input and output. The thing that you want to get, you want to calculate, you want to predict is going to be your output. The thing that you use to make that prediction as input will be your input variable. Okay. Now, to estimate Y using linear regression, we assume the equation as this. Y of E, which is the estimated value of Y, will be equal to beta multiplied by X plus alpha, where Y sub E is the estimated or predicted value of Y based on our linear equation. So what is X? In not just in our example, overally, what is X?
Independent variable.
Or our input. And what is YE?
Your dependent variable, your output.
The output. So what about beta and alpha?
Alpha is going to be your y-intercept, right? Yeah. And then your beta is your slope.
We are describing a line. That is why it is called a linear regression. And in order to describe a line, you need a slope and you need an intercept. That is going to be your beta and alpha. Our goal is to find a statistically significant values. Caden, this is specifically for you. Our goal is to find the statistically significant values of the parameters alpha and beta that minimize the difference between Y and YE. Why do we want to do that?
Because we're going to estimate via Y to predict what our future Y values will be, and the closer they are to being correct.
So what do we call the difference between Y and YE?
Error?
Exactly, thank you. And who would like to have a large error when they can have a smaller one? People who like to see the world burn, and we are not those. So we want to have a smaller errors. So our goal is to minimize the difference between Y and YE. If we are able to determine the optimum values of these two parameters, then we will have the line of best fit that we can use to predict the values of Y given the values of X. Do you remember that in our previous sessions, we had a bunch of points and then we would fit a line and we would describe that fit? Okay, I have one yes from Jalissa, one yes from Abby. Okay, one from Wally. Keep answering me. And how would we change the line on what basis would we change the line? Slope and intercept. Yes, those were the numbers that we would use to make it go up, down, or change the slope. But when would you know when to stop? When would you know that you have the best position?
You mean visually?
So that's what we were doing, right? In our previous attempts, we were assessing it visually. Would you feel comfortable with that? Could you be absolutely sure that there are no better slopes and intercepts for that line? So depending on a visual assessment is not the safest way to go. That's why we need a better numerical method to find those two parameters. So the question is, how do we estimate alpha and beta? We use a method called OLS, or ordinary least squares. So before I proceed and repeat this term again, does OLS stand for anything offensive or weird in your slang language?
I don't think so.
Okay, good. So, cool. Do you remember these red points, red dots?
Yeah.
Do you remember this blue line that we would use to fit? Okay. So at every point, the difference, the distance between the point and the line is the error of prediction. Do we agree on that? Okay. In an ideal world, we want this blue line to go through the line, to go through the points, which means we would not have any of these green lines, indicators of error. So looking at these 4 points, do you see any ways that you can hit all of them with one straight line?
No.
Okay, so one way or another, if you are using a linear regression and a linear model, you are going to have some error. But what you need to do is you need to make sure that you are getting the minimized error. Nothing more than the minimized error. Okay, how do we do that? The objective of the least squares method is to find values of alpha and beta that minimize the sum of the squared difference between y and ye. What is the meaning of sum of the squared difference? So we have one difference here, we have one difference here, one difference here, and one here. Sum of the squared difference. So I'm going to calculate this, take it to the power of 2, plus this to the power of 2, plus this to the power of 2, plus this to the power of 2. Why am I taking that to the power of 2?
Probably because you don't want negative and positives.
Exactly, because an error is an error to me. I don't care if it's an over prediction error or an under prediction error. I don't want to have errors and I want to minimize them. So I take them to the power of 2 to get rid of positive and negative signs, and then I sum them up because I care about the broad range, not just 1 point or 2 points. We will not go through the derivation here, but using calculus, we can show that the values of the unknown parameters are as follows. So this is how we calculate beta and alpha. We have a formula for beta, which is calculated based on the x and y's of each point and the average x and average y. And once we calculate beta, we just put it in the equation and we calculate alpha. X bar is the mean of x values, y bar is the mean of y values. Beta is simply the covariance of x and y. Have you heard about this before? It's okay if you haven't, but just let me know. Okay, I have one no in the chat box.
It sounds familiar, but I can't recall.
So what is the closest word that you have heard to covariance in this class?
Correlation?
What else?
Variance.
Exactly. Thank you. So I would say variance is closer to covariance. So variance is defined for each variable with respect to itself. Covariance is defined for each variable with respect to another variable. Covariance, like the co-op mode. So the formula for covariance is this. And here we will just briefly explain what is happening with covariance. In probability theory and statistics, covariance is a measure of the joint variability of two random variables. If this is a little weird, don't worry about it. We are basically saying that if the greater values of one variable mainly correspond with the greater values of the other variables, we are having a positive covariance. For example, let's have a look at these two sets of numbers. Would you say that the greater values of a speed are happening at the greater values of time?
Yep.
Would you say that the smaller values of a speed are happening with the smaller values of time?
Mm-hmm.
This means a positive covariance. Now, if this would be reverse, so let's say shooting a ball. It can be a football or a soccer ball. I don't want to get into that again. So at the early seconds, the ball will have a higher speed, correct? The more time will pass on, the slower the speed gets until the ball stops. So in that case, I can say, the biggest values of the speed of the ball are corresponding with the smaller values of time, correct? Give me an answer, come on. Okay. In that case, we are dealing with a negative covariance because greater numbers of A are associated with the smaller numbers of B and vice versa. The sign of the covariance, therefore, shows the tendency in the linear relationship between the variables. The magnitude of the covariance is not easy to interpret because it is not normalized and hence depends on the magnitudes of the variables. So if you're dealing with huge variables, you will get huge covariances. If you're dealing with small variables, you will get a small covariances. You can only pass a judgment on the sign of the covariance, whether it is positive or negative. So the normalized version of the covariance, which is known as the correlation coefficient, shows by its magnitude the strength of the linear relationship. So the cool thing about the correlation coefficient is that you can get two things from it. First, the sign, which will tell you whether you have a positive relationship or a negative relationship. And then the magnitude, which, when it is closer to 1, it is a stronger relationship. When it's closer to 0, it's a weaker relationship. So let's have a look at this 3 plots. In the first one, with bigger values on the x-axis comes bigger values on the y-axis. Do we agree on that? This is a positive correlation, also a positive covariance. How about this one? Would you say that with bigger values of the x-axis, you're getting bigger values on the y-axis? It seems that the values on the y-axis are between this range regardless of your x values. This means that there is no correlation between the two. How about this one? Would you say that for bigger values on the x-axis, you are having the smaller values on the y-axis? This means a negative correlation. Now, The correlation coefficient is the normalized form of the covariance. And we use it to measure how strong a relationship is between two variables. There are several types of this specific coefficient, but the most popular is Pearson's correlation, also known as Pearson's R. This is how we calculate it. You don't really have to know this formula. But in a case like this, you get a value between -1 and 1. A Pearson's R equal to 0.4 means that you have a positive linear relationship, you have a positive correlation, but its strength is 4 out of 10. In this one, you have the same strength, but in the other direction. This is a negative relation. And in a case like this, you get an R equal to 0, which means you have no correlation. Do we feel comfortable about covariance and correlation coefficient and how to interpret it?
For sure.
Yes.
Yes, no.
Do we have any questions about this? Okay, now let's have a look at the problem from the exam. Let's create a data frame with these two numbers. I'm importing NumPy, Pandas, statistics, and Matplotlib. My time, a list, my speed, a list. I'm putting them together and I'm getting this as a Pandas data frame, the first step. Now, I am going to explore the data with
Describe.
the describe function. So, Caden, tell me what you see.
Well, in both columns, we have 11 things. The mean of time is 5, and that's nearly meaningless. The mean of speed, however, is 43.1. That's useful. Standard deviation of speed is 41.2. I see our min, our maximum. I can calculate the inner quartile from that. That's about it.
Okay, thank you very much. Let us go on and calculate the variance for time and speed based on what we have. Do I have a volunteer who wants to explain this? I can ask Aaron. Are you there?
Yes, I'm here.
Awesome. So can you explain what is happening in this code cell?
You're using from statistics the variance program, I guess.
Function.
Function, and then you're printing what you like define that function to be as in your print.
Okay. And what is the variance for each one?
For the first one is 11, and for the second one is 1697.78.
Awesome. So thank you very much. The first question is there a relationship based on covariance and correlation between time and speed? So I'm going to use the COV function from Pandas and calculate the covariance for my variables. Do I have someone here who wants to explain this for us? Wally, are you there? Nope.
He's in the chat.
Oh, yes. Your microphone is messed up. It's all right. I'll ask someone else. Deborah, are you there? Nope. Jordan.
Yes,
Okay, you are there.
I am here.
So tell me what you see in this little table.
I see that it's a total time and total speed, right?
What do you mean total?
Or I guess the average speed and average time.
I'm calculating the covariance for my two variables, time and speed. So if you notice, Between time and time, and between speed and speed, I have two numbers that should be familiar to you. Right?
Yes.
So the covariance of time with respect to time will be the variance of time. And the covariance of a speed with respect to a speed will be the variance of a speed. Now, what you need to pay attention to is the covariance between a speed and time. What does this number tell you?
There's a positive correlation, or positive covariance rather.
Okay, you see a positive covariance. What does it mean?
Upward trending slope.
Come again?
That our slope is upwards trending.
Okay. What do you think about the strength of that relationship?
I don't think we can judge it here because it depends on the magnitude of our variables.
Okay, so I am telling you that you have 131.75 covariance between a speed and time. What does that mean?
I thought you said that we can't make any judgments other than positive or negative at this point.
Good. What do you need to make a judgment?
Pearson's R.
Or any other correlation coefficient, correct. So that's why I go on and I use this function, CORR from pandas again, and I choose method to be equal to Pearson, and I get a similar table for different content. Now, what do we see here?
We see that they have a strong correlation.
Why do you say strong?
Well, because when we have a magnitude value of 1, that means that it's super strong. So like the 0.964 blah 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 is really close to 1, so that means that they are really strong.
Exactly. So similar to what Caden and Abby said, looking at covariance, we can only judge on the direction of the relationship and say whether it is positive or negative. Looking at correlation coefficient, we can say that if it's positive, we are dealing with a positive relationship. And if it's close to 1, it is a very strong relationship. If it's close to 0, it is a very weak relationship. Okay. Do I have any questions up on this point? Is everything clear?
I have a question real quick.
Sure.
Why is it using the left top number with the time, but it's using the bottom right number with the speed?
Are you talking about this table or this table?
The one on top.
The one on top. Okay. So this basically tells you that the calculation is happening between which two variables. If you calculate the covariance between time and time, you are basically calculating the variance of time. If you calculate the covariance between time and the speed, you're calculating this covariance, which is equal to 131.75. Now, the covariance between time and speed is equal to the covariance between speed and time, because you can switch places, nothing will happen. So that's why you're getting the same number here as well. And then the covariance between a speed and a speed will basically be the variance of speed.
Okay, that's kind of a dumb question. I'm sorry about that.
No, don't worry about it. Did you get it now?
Yeah, I got it.
Awesome.
Thank you.
There's no such thing as stupid question, guys.
Well,
Thank you.
teach enough for long enough times, you will see that there are those questions. Just kidding. I'm sure that Dr. Cleveland has lots of experiences with that. Okay, so are we sure that we feel completely comfortable with calculating covariance, interpreting that number, calculating a correlation coefficient, Pearson's R, and interpreting the results? All good? Awesome.
Yes.
Now, thank you. Let us go on and do linear regression with primitive Python. To estimate y using the OLS method, we need to calculate x mean, y mean, the covariance of x and y and the variance of x before we can determine the value for alpha and beta. In our case, x is time and y is speed. I have to ask this again. Why? Okay, now you're freaking me out. Why x is time and y is speed?
I mean, I don't know if you mean generally. In general, in a time series graph, x is the independent variable.
Do you remember when I asked at what time the speed of the ball will be 200 meters per second? In that case, what will be your x? What will be your y?
The other way around or whatever.
So Wally said we are judging the speed based on time, which is correct. You're trying to predict the speed, so speed will be your y, and your input is time, so time is going to be your x. Time is going to be your x. Okay. Any questions? So let us move on and get all the things that we need. Let's calculate the mean of x, mean of time. Let's calculate the mean of y, or mean of speed. Calculate the terms needed for the for our numerator and denominator. xy COV is going to be calculated like this, and then the variance is going to be calculated like this. And now we can calculate our what is happening in the chat box?
I'm not sure, to be honest.
So I would really appreciate it if you stick to the topic. If you have the energy, please spend it with the lab. So we are going to calculate beta and alpha. How? We have the formula right up here. So we are basically applying this into our code cell. Where were we? Okay. Beta is going to be calculated as this. And then once we have beta, we just put it into our linear equation and we calculated alpha. So these are the values that we get for alpha and beta. So which one was the slope? Which one was the intercept?
Beta was the slope, alpha was the intercept.
Okay. When you have a slope of 11.98, what is the meaning of that? Does that tell us anything?
For every 1 increase to our x, our y increases 11.98.
Exactly. Would you say that is a positive relationship or a negative relationship?
Positive.
Was it something that you kind of expected to happen?
Yeah.
Why?
Because our R value told us that would happen.
Exactly. So that's what I wanted you to notice. Based on the information that you had, there are certain checks that you can do very briefly, very quickly, and just visually. If you had got a negative slope at this point, it should have been a red flag. There was definitely something wrong in the code, because you just looked at Pearson's R and you saw, okay, there's a strong positive relationship between time and speed. Why am I getting a negative slope? Okay, thank you very much. Now that we have alpha and beta, we now have an estimate for alpha and beta, and we can write our linear model. So the estimated value of y will be equal to whatever time we have as input multiplied by 11.977 minus 16.786. This is our linear model, and we can use it to predict speed based on time. Now, we can make predictions. So Do you remember the time values that we had in this table? Let's feed these to our linear model and see what numbers we will get. So for time equals 0, we are getting a speed of minus 16.8. What does that mean?
Oh, it's our intercept.
It is your intercept. So looking at it from a physical perspective, at time equals 0, you have a negative speed. What does it mean?
The
Means our
are
model.
gonna get error.
That sounds like an error. What did you say, Caden?
It means our model doesn't work very good at low numbers.
Okay, that is another good observation. So what would you suggest? Let me change the question. If I'm interested to have assessment of the overall performance of my model, what is some way that you would suggest? No suggestions for me?
Can you repeat the question one more time?
You come out and you tell me I have created you this linear model. And I ask you, can you show me the overall performance? Show me something that I can understand the overall performance of your model.
So I would say you would use the function you introduced, the .cov thing.
Can you repeat that?
Use the function .cov.
So you want to compare the COVs from the model and the observed COVs? Is that what you want to do? Wally, thank you. Yes. One way of assessing the performance of the model is to look at the graph, the visual assessment, something that we were doing before. So let us move on. Plot our prediction y-pred against the actual values of y. So the blue points were the actual observed values measurements that we had, and this red line is our linear model. Now, how do you feel about this model?
Pretty good.
Oh, really?
Oh,
To an extent, pretty good.
So we just discussed that your model tells us that at time equals 0, the ball was actually going backwards with a speed of 16 meters per second.
listen, he's doing his best. I think you're being a little judgmental.
Okay, yes, there you go. Actually, the very first time that we were judging a model visually, Harper said something pretty wise. Do you remember that, Harper? You say so many wise things, so how can you keep track, huh?
I think it was something along the lines of, you know, looks pretty good to me. It's close enough at least, and it doesn't need to be super exact. So like, yeah, I mean, when our model shows negative, we're like, well, we can't go negative, so we don't really care about that. The rest of it lines up pretty good.
Unless you are forced to do it, do not try to describe something with a single word. We don't have to come out and say, this is great, this is the worst, this is garbage. We don't have to do that. So we can actually look at this and say, okay, it seems to be doing pretty well for the higher ranges. It seems to be doing closely for the middle ranges, but for very low numbers, it is producing unrealistic outcomes. See, this is a way more fair assessment. And if someone is not looking at this plot, what you are describing is more informative. Do we agree on that?
Yeah.
Yes.
Okay. So the red line is our line of best fit. We can see from this graph that there's a positive linear relationship between x and y. How can we see that?
Either visually by seeing that it's positive slope or looking at our value.
Exactly. Now, using our model, we can predict y from any values of x. So if someone asks you at time equals 20 seconds, what will be the speed? You can simply feed 20 as your input, as your x, and get this speed. That's how we use linear regression to predict as a predictive model. So in the example that we covered so far, we have used linear regression for two purposes. Can you name them?
To normalize data.
Did we normalize data?
Or to make a model.
Okay, fair. We made a model. We used that model for two purposes. Can you name both of them or at least one of them?
We can predict other values outside of the
Okay, so predicting was one of the things that we did. And the other one? I'm just showing it to you.
The correlation.
We used it to describe the relationship between our measurements. So you can use it to explore your data and the relationship between variables, and you can use it to predict one variable based on the other. Fair enough? Yes, Wally, we did graph, and we used the graph to explore and investigate the relationship and compare. So both of those answers were valid. Any other questions? Now, we don't really have to go through all this for linear regression. We can actually use the stats model and use the OLS method built in to very quickly fit our input and output data and get the parameters, get the alpha and beta. So if we run this, we are basically calling stats model.formula API as SMF. And from that, we call the OLS function. And the syntax for this is a little different from the things that you have seen before. Have a look at this. First question, what do we call this?
A tilde.
Thank you. Yes, it has a very fancy French European kind of style name to it. I really like it. So what does this mean? Speed tilde time.
Speed is approximately equal to time.
Not here. If you see that in some kind of mathematical representation, you could go with that, but not here.
Is it just straight up equals?
What this means is that you want to predict speed based on time. Or you're basically introducing your input and output by this formula. That's how this function and many other functions in the machine learning business understands formulas. Output, tilde input or inputs for that case. And data equals data. What does that mean?
Is this a coincidence that our frame is named data?
Exactly. So the first one is always data equal. The second one is the name of your data frame, which in this case happens to be data. It could be anything else, but the first data should always be there. So we first initiate our model, and then we use the fit function to fit it to our data. And as quick as that, we do not have to calculate alpha and beta anymore. We can simply ask this params on our model, and it will give me the intercept and time. These two numbers, are they familiar? Are they the same numbers as we calculated?
Yeah.
So just as a confirmation, you do not have to go through all that trouble to calculate all the things. You can just fit the model here. So again, we can get a plot and we can get the same results and the same fit. So as the last question, how do you feel about this predictive model? Will you trust it?
I'll keep my faith intact.
About as far as I can throw.
So you would trust it as it is.
I mean, yeah.
It depends on what I'm using it for.
Okay, that is a very good perspective. Can you please elaborate?
So like, it depends on like the job that I'm, like certain levels of precision. You know, like there's like aviation precision, and then there's like car precision where, you know, you can only be off, the models can only be off by like 1/1000th of an inch or something crazy like that, versus like a car where you can have like 1/8 of an inch. So
okay, so let me ask you this. Under what circumstances, for what kind of applications would you recommend this model to me?
I would say just general purpose, but nothing that requires FAA standard 7 on.
Okay, that was pretty big. So anyone else who wants to share their ideas?
I would say
You have already said that you trust it and you have faith in it.
yeah, I like because I guess because we already have units, we would use something that has velocity, so something that's moving, like it increases its speed at every second. So yeah.
So if I come out and say I trust this model between the range of 2 to 8 seconds, and I don't trust it for anything below 2 seconds, would you like my assessment of the model?
You could get a little higher, but yeah.
So that's what you need to do. You may come up with a model that does a terrible job for low numbers, but does a terrific job for high numbers. And if you want to use that model for high number analysis, then that model will work for you. You just need to be aware and make other users aware certain areas that this model is trustable and some other areas that this model should never be used. Again, for the case of water resources management, sometimes you care about floods and extreme floods. Sometimes you care about droughts and no flow periods. If a model is doing an extremely good job in detecting extreme high floods, but tends to over predict no flow events, then You can use it for flood detection, but you can't use it for drought detection. So just try to be realistic when it comes to modeling. There will be no model that can give you 100% accuracy over everything. That's not going to happen. So you're trying to capture parts of reality using your model. And if it does a good job on some parts of it, then we will use it for those parts. Okay, any questions about the regression problem that we covered in the lab so far? Okay, I have left a quotation at the end of this lab. I'm going to show it to you now. Working an integral or performing a linear regression is something a computer can do quite effectively. Understanding whether the result makes sense or deciding whether the method is the right one to use in the first place requires a guiding human hand. When we teach mathematics, we are supposed to be explaining how to be that guide. A math course that fails to do so is essentially training the students to be a very slow, buggy version of Microsoft Excel. Now, this is not a mathematical course, but it is very important for me and for Dr. Cleveland that you understand what you are doing with the model. Simply just putting information into your notebook, fitting a model using the stats model and getting the results is not what we want you to do. We want you to be able to understand the results and be able to interpret the performance of a model. Now, after this, do you feel comfortable about what happened in the first example and how we interpreted the results of this linear regression model? Give me a yes in the chat box so that I can move on.
Yes.
Okay. Okay. Example 2, advertising and sales. This is a classic regression problem. We have a data set of the spendings on TV, radio, and newspaper advertisements, a number of sales for a specific product. We are interested in exploring the relationship between these parameters and answering the following questions. Can TV advertising spending predict the number of sales for the product? Can radio advertising spending predict the number of sales? Can newspaper advertising spending predict the sales? Can we use the three of them to predict the number of sales from the product? This is a case of multiple linear regression. We will talk about it. And then which parameter is a better predictor of the number of sales for the product? So, the first step is to read in the data set. You have this file, or you can download it from the server, advertising.csv. Dr. Cleveland also put it in the chat box at the beginning of the lab. So if you scroll up, you can find it there. And I use the head function for
to print the first few rows of the data set.
Exactly. How many columns do you see? 5, 08, 4. Okay. And what are those columns? TV, radio, newspaper, and sales. We have the spendings on TV advertising under this column, on radio advertising under this column, and on newspaper advertising on the third column. And this is the amount of sales. Now, we are going to use the describe function on this data set. I want someone to volunteer and explain what is happening here.
Can you say that again? Sorry,
I want a volunteer to come out and tell me what they see. after we run the describe function on our data frame.
I'll volunteer.
Okay, cool. So what do you see?
I see the count. There's 200 items in each column, I guess.
Okay.
The mean, the standard deviation, and then you get the interquartile range right here. I mean, at the 25 to 75. You get the median, and you get the max and the min.
Okay, and what can you understand based on comparing these numbers? For example, if you compare the numbers under TV with numbers under radio, what will you understand?
I see that the mean is different, really different actually between both of them.
Why do you think that is happening?
Maybe because they're different data sets, or they don't really correlate as much.
Or simply because TV advertising is much more expensive than radio advertising.
Oh yeah, that too.
Because people don't like to listen to radio anymore, unfortunately. But you always have people who like to eat their burgers while watching Liberty, 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 Liberty. So TV advertising tends to be more expensive. What else can you tell me? What do you see when you compare radio and newspaper?
That more people rather read newspaper than listen to the radio.
Or you're telling me that newspaper advertising is more expensive, correct?
Yeah. Yes.
Okay, thank you very much. Now, we are going to define our columns separately. So we will have TV, radio, newspaper, and sales as NumPy arrays. We are going to calculate the covariance. And this time, Lane, are you there?
Yes, sir.
Okay, can you tell me what you see here?
Kind of just looks to be like statistics. I'm a little confused though because it has the same like titles on both rows and columns.
Uh-huh.
So
what function did I run?
Is it cover?
That's
covariance.
Exactly. That's a COV function that stands for covariance. So the numbers, the statistics that you're seeing are covariances calculated between your variables. What can you tell me? What do you see? What do you understand from this?
Well, it's almost kind of like, I don't want to call it a mirror, but it's kind of just like
it is a mirror.
Right? I mean, that's the best way I could use to describe it.
Yeah, because the covariance of A and B is equal to the covariance of B and A. So with respect to the main diagonal axis, everything is mirrored. That is correct. What do you understand from the numbers?
Well, it looks like it's saying that the TV sales were 350, radio 44, newspaper 25, but I'm a little confused on what sales for sales means or TV for TV, because these numbers aren't replicated, but they don't make any sense. Like,
so the covariance of TV and TV is equal to the variance of TV. The covariance of sales and sales is equal to the variance of sales. But let me ask you this. TV and radio have a covariance of 69.8. What does that mean to you?
69.8, radio for TV, TV for radio. Maybe like the difference in sales. I'm not sure.
Okay. Do I have anyone else who wants to venture a guess on this?
Can you ask the question again?
When you see the covariance of TV and radio equal to 69.86, what does that number tell you? What can we infer?
Is that how close they are?
So based on this number, do you think they're close or they're far?
They're close.
Okay. Anyone else who wants to venture a guess? Harper says it's positive. Duh, it is positive. What does that mean?
So I mean, that means they have a positive relationship.
Uh-huh.
And,
Yes. So basically, all you care about when you look at the covariance numbers is their sign. And as Harper said, when you have a positive number for covariance, that means that you have a positive relationship. So do you see any negative numbers in this table? So that basically means that all of your variables have some degree of a positive relationship with each other. What can you tell me about the strength of these relationships? Are they strong? Are they kind of weak? Are they somewhat strong? Are they completely weak?
we need more testing.
Yeah, we don't know yet until we do the correlation coefficient.
Exactly. So in order to get that information, you need one step further, and you need to look at Pearson's R or some other correlation coefficients. That's why we do this. Now, who wants to tackle this table for me? Let me ask Sarah Duello.
Yes.
How are you doing?
Tired.
Okay, I see. So can you tell me what you can understand from the table of Pearson's R? This table.
That okay, sorry, you had the one above it highlighted.
Yes, I thought that I'm confusing you, so this one.
Yeah, we can see the correlation. They're all positive numbers.
Okay. What about the strength?
We see the diagonal that TV has a 1-to-1 correlation with TV, radio has a 1-to-1 correlation with radio.
Which makes sense because we're comparing it to itself, okay? So let me ask you this. What are we trying to predict? What do you think is our target variable here?
Not positive. Or not,
No.
Sure. I mean.
Which, between TV, radio, newspaper, and sales, which one do you think we can consider as a target?
Well, we can see the highest correlation between TV and sales.
Okay. Let's say that sales is our target. If you want to tell me which one of the variables have a stronger relationship with sales, which one would you pick?
I would say TV.
Why?
Because it has the highest correlation of the three.
It has a 0.78, which is quite close to 1. And based on this, you can say, okay, there is a strong linear relationship between TV and sales. What is the next one?
The next would be sales and radio.
And the next one?
And then sales and newspaper.
Okay, so based on this, if someone comes out and asks you, should I, if I'm interested in selling more, should I spend money on TV, Liberty, or should I go for newspaper, or should I go for radio?
You would want to go with TV. Because
exactly. Okay.
Correlation.
Thank you very much for playing. Now, let us go on and answer the first question. Can TV advertising spending predict the number of sales for the product? I'm going to fit a linear regression model using the stats model. I'm going to get intercept and slope, and I'm going to apply that, plot it, and get this. Now, this is a different plot, isn't it? Who wants to talk about it?
So based on what we got for our covariance, we can see that it's a strong relationship, but it's a little bit weak.
Why would you say that it's weak?
Because like the covariance value was 0.78ish.
That
And
was not the covariance, that was the correlation
I
coefficient.
mean the correlation coefficient, yeah. So
a correlation coefficient of 0.8 is not that weak, is it?
it's not that weak. It's not that weak, but it's also not too strong. So it's kind of
Okay.
like, so like the number we got for the coefficient thing, it was like somewhat strong.
Okay, tell me this. Based on this graph, and this is a question for all of you, so think about it. Based on this graph, if I tell you that I want to spend $50,000 on advertising, on TV advertising, how much sale you think I will have?
I kind of feel like it'd be hard to tell because it kind of turns into like you can't, I don't know how to explain it.
Jalissa, if it wasn't a hard job, I wouldn't pay you for it. So I've come to your office, to your company, and you have shown me this plot. And I don't know what this is, so I ask you, tell me this. If I spend $50,000 on TV advertising, liberty, 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 how much sales can I expect? What number will you give me?
I'm really not sure. Harper says 9, and I don't know where he got 9 from.
Because he's assuming that this is 50,000, which is correct.
Oh,
So
I didn't know that was in thousands. I thought, oh, I don't
yes,
know.
yes, because it is a little unrealistic to go with $50 for TV advertising. No one is going to even
You're right.
spit
Okay.
on you for that. So let's assume that everything is in thousands of dollars. Now tell me what you think.
I'd say 9.
You would say 9.
Yeah.
Okay, 9 units of sales. What if I ask 100,000?
Probably like 11, 10.
Are you reading the red line or are you reading the blue points?
I'm reading the red. Is that wrong?
Not necessarily. You are the expert here. I'm just listening to you. So what about 300,000?
Like 21. Am I supposed to be reading the red one?
No, you're fine. You're fine. Just keep doing what you're doing. Now, I've asked you 3 questions and you gave me 3 numbers, right?
Yes.
On which one of them do you feel more comfortable? Do you feel more confident? On the first one, where I said 50,000, you told me 9, correct?
Yes.
What would be the worst case? Like, what was the number if you were completely wrong?
I don't understand the question.
So you looked at the red line and you told me 9, correct?
Yes.
How off could you be?
Oh. Pretty off.
Give me a number.
How off I would be?
Yeah, for example, you said 9, it could have been 12 or it could have been 8, right?
Uh-huh.
So, as the person who wants to spend the money, if I tell you I want to spend 50 and you tell me 9, and then I end up with a 12, will I be happy or will I be sad?
You'll be happy.
I will be happy. Wonderful. If you tell me 9 and if I end up at 8, will I be happy or will I be sad?
Sad.
Okay. So there's a difference between the 9 and 8 in this case, right? Let's move to the next one. $150,000. The number that you gave me was
Oh, I don't remember what I said for that.
You can look at it again.
Like,
You were not just making up numbers, were you?
no, I'd
So,
say 15.
15.
Okay, 15.
Okay. With 15, what is the furthest off you can be on top and on bottom?
Probably like, are you asking like the difference? I just don't really understand.
Yes, you told me 15. So let's say the red line is at 15. What is the furthest that I could be in?
Like 9.
9. And what is the furthest up that I can be in?
Like 17.
17. Okay. So if you tell me 15 and I end up being at 17, I'm happy, correct?
Yeah.
But if you tell me 15 and I end up being at 9, I'm not happy. Right? So between this case and the previous one, what are your risks for making me unhappy? Which one is riskier?
150.
Exactly. So let us move on to 300. What number will you give me for $300,000 of investment?
Like 20.
20. What is the furthest low that you can be?
Is it not okay? Am I looking at those 2 dots that are right on the line? Should I not be looking at those? Is that off?
Yeah. Can I be further, or can I be like here?
Yeah.
So what is that number? 15? 12?
12, yeah.
Okay. And anything above?
Like 23.
23. Okay. So as a client, I come to your office. You look at your red line and you tell me if you spend $300,000 on TV advertisement, you are going to gain 20. But I end up with only 12. So you are 8 units short. Do you think that I will ever come back to you for business?
No.
No.
No, not after that.
So between these, yeah, that's RIP. Okay. So between the 3 questions that I asked and the 3 answers you gave me, on which one of them do you feel more comfortable?
50,000.
Why?
Because there's less error there, I guess.
Exactly. Because if you notice in the left side of this graph, your points are much more closer and compressed. But as you go to the right, you are having wider variability. So if I ask you, on what areas do you trust this model better? You would probably come out and say for values less than 150, this model is doing better than for values above 150. Fair enough?
Yes.
Thank you very much for playing. This was a very new game. Thank you. So let me see what I have in the chat box. You would get 12,000 sales with a large margin of error. Not very okay. So basically, this linear model that we have here could be a good model for conservative investors and not for the ones that want to go crazy. Because if someone spends $300,000 on something, they don't want to be off by half of 20. That's not good business. Okay, so let us do the same thing for radio. And this time we are going with sales steadily radio because we are predicting sales based on radio. And we are going to graph that and look what we have now. Do you like radio better than TV? I have a few no's coming up in the chat box. And why don't you like it?
It's terrible.
It's too much variability. It's really hard to be comfortable about anything at any parts of this. So you may spend $30,000 and get 20, or you may get 5. This is a huge range of variability, and it gets worse as you go on. So too much error, exactly. Now, what about newspaper? We're going to do the same thing. Sales, newspaper, we're getting the parameters, we're fitting the model, and we are getting the graph. Lovely, isn't it? It's even worse than the radio. And did we expect this to happen? Did we expect TV to be a better predictor?
Yes.
Why?
Because they brainwashed
It had the higher correlation.
Exactly, because of the higher correlation coefficient. Exactly. Now, this is the time for the final piece of the show. Can we use the three of them? Can we, at the same time, can we look at newspaper, TV, and radio spendings and predict the sales? This is a case of multiple linear regression. This is simply a linear regression model with more than one predictor, more than one input. This is how we model it. So you, instead of y equals to alpha plus beta x, you will have beta 1 x1 for TV, beta 2 x2 for radio, and so on. So in this case, we have 3, so we will have also beta 3 x3 for newspaper. Multiple linear regression from the scikit-learn package. We're going to use that. We define our predictors. Then we define our x and y. And then we fit the linear regression model. We get alpha and betas. Notice that we have one alpha, which is the intercept, and we have 3 betas as our slopes. One slope per variable. Therefore, our model can be written as sales is equal to 2.938 plus 0.046 multiplied by TV plus 0.1885 multiplied by radio minus 0.001 multiplied by newspaper. Do you realize how small this number is? Okay. And we can simply use them to predict number of sales. Now, kind of a little question for the last part. Look at the beta numbers and tell me, what can you understand from them? Which one of them is a better predictor, is a more important predictor?
Well, judging by this, I'd say radio.
Yeah.
Okay, and Julius also says the second one. That is quite interesting, isn't it?
It is.
So
It had a higher value.
Simply looking at correlation coefficients doesn't mean that when you combine variables, you're going to get the same level of importance. Because when you are looking at correlation coefficient, you're looking at them one by one. TV and sales, radio and sales, newspaper and sales. In this case, you're looking at the 3 of them against sales. So keep that in your minds. For references, there are some interesting weblogs that you can read. There are some interesting videos. These are the ones that I used for putting together this notebook. And as an exercise, I've asked you linear regression, yay or nay. List some of the pros and cons of linear regression and make sure to cite any resources that you may use. Thank you very much for paying attention and playing games today with me. I am going to stop sharing my screen and passing the host back to the boss.
All right, welcome back for me. And I am the host now.
Yes, sir.
So we are done. You get out a little bit early today, which is probably a good thing. And you have seen everything there is to know about linear regression except how to do it. And you'll get plenty of chance to do that over the next few meetings. It's a complicated sounding word. It's actually reasonably easy to wrap your brain around. And the whole purpose, as Farang said, is that we have to interpret the results. We can't trust the machine. We shouldn't trust a machine to do that. And it's all going to be problem dependent. So try to get comfortable with looking at the output. We heart coding.
No, it says we are coding, so.
Cool. And so I showed you the classical linear algebra way, and Farang showed you computationally no different, but probably a superior way to interpret your results. And that's all I have for today. So you're all free to go. You have a homework assignment that's due next Wednesday, exercise set 9, which is on A/B testing, and darn it, what was the other thing?
Confidence intervals.
A confidence interval. And it's simple. It's literally out of the lab on those topics. You have this lab due next Thursday. And I think that's all the outstanding due items that you have. So have a great weekend. Will, Sean, if you're still there, if you stay on the line and then everybody else disconnect, he has a office hour request and it'd just be easier to leave the thing running. I got to turn off the recorder. So let me do that. So I'm stopping.